All right, it's 8:30. Let's go and get started. All right, good morning, everyone. How's everyone doing today? Okay, midterms, it's a stressful time, so hang in there. I always tell people that midterms, when midterms come around, I know kind of the tempting thing is to just study all night, but trust me when I say, I think the thing that's actually most valuable to you when you're taking midterms is just getting a good amount of sleep to make sure you're eating well. Keeping up your physical health, I think, is underrated when you're studying for midterms. Make sure you guys are taking care of yourself. I remember when I was a student, when midterms would come around, it was so dumb thinking back on it. My friends and I, we would always compete, not really compete, but we would say like, oh man, I stayed until like 2 a.m. studying for the exam. Oh yeah, you stay up to 2 a.m. I stayed until 3 a.m. It was like, we got weirdly competitive about it. And then we look back like, I was so dumb. So like now that I'm in my 30s, we all have weird health problems because of, our bad health habits in college. So I would encourage you guys, take care of yourself. The midterms will come and pass, but your physical health is something that, is going to be affecting you later on in life. And so, definitely take care of that. So with that said, we have a midterm coming up in this class. And so it's going to be next Thursday. So Thursday, March 9th, that's not this Thursday, that's going to be next Thursday. Okay. And here's some information about the exam. I haven't written the exam yet, but I do know what I want to do with the format. So the format is going to be kind of, the exam is going to be split into kind of two sections. And so the first section is going to be conceptual problems, okay? And so that's going to be about 40% of the points. And so I'm planning to ask 4 questions. And so that's very similar to all the homework so far. And so if you look at the homeworks, problem 1 is always conceptual problems. And so what I imagine for these problems is that, I'm going to ask you a question based on the concepts in the class. You won't have to do any calculations. And you would answer the questions with, 2 or 3 or 4 sentences. Maybe I'll have you draw a picture, depending on the question. Okay? And then the rest of the exam, which is going to be 60%, that's going to be all the problem solving. So all the ODEs that we've okay. And I'll give you another hint. We've had we're gonna have 3 homeworks that's going to be on this exam. Homework 1, homework 2, homework 3. And so for the problem solving portion, you can probably expect 1 problem that's similar to each one. So 1 problem based on homework 1 content, 1 problem based on homework 2 content, and 1 problem based on homework 3 content. Okay, so all the homeworks will be kind of well represented on these. I think this class kind of it kind of fits pretty well into that. Okay. All right. So what you can bring for the exam, first of all, you can bring, please bring a writing utensil, please bring a pencil, pen, whatever you feel most comfortable with. You can bring a calculator. I'm not that picky about the format of the calculator. You're only really going to need it for just basic arithmetic, but any type of calculator will work. Okay. And probably what you guys are most interested in is the cheat sheet. So I'll let you guys bring a sheet of notes into the exam. So that's 1 8.5 by 11 sheet of notes. You can write on both sides, front and back. Doesn't matter to me. You can write it. You can type it. Whatever is most comfortable for you. The only thing that the only requirement that I have for the cheat sheet is that you can read it during the exam. And so I don't want people going like Senator Chang from Parks and Rec, or I forgot to show Community. During the exam, okay, and no magnifying glasses. So I say that you think it's silly, but it's happened before that someone printed a cheat sheet in like 3-point font and had a magnifying glass and try to read things. So none of that, please. So please write your cheat sheet in somewhat legible form so you can read it without any help. Okay. All right, so what am I providing you for the exam? So there's a study guide on Canvas that is already up. And so if you look at the weekly page for week 6, which is what we're in right now, you should see a file at the bottom called Study Guide for Midterm 1. So please definitely take a look at that. I'm also planning on filming a review video on Monday, or recording a review video. Okay. And so I like to do this before all my exams. And so I like to record a video. Usually it's about an hour long. So it's almost about the same length as a lecture. And I just kind of review all of the important content. Okay. And so for this class, because this class, a lot of it has to do with the problems. I'm probably going to work out at least 3 examples on that review video, probably examples that we haven't seen yet. 1 from homework 1, homework 2, homework 3. Okay. And so you can look forward to that on Monday. So I plan on recording that offline and then posting that on YouTube to help you guys out with the study. Okay. And so regarding the study guide, please use the study guide. The study guide is really there to kind of help organize your study. Okay, so what I've basically done for the study guide is all the learning objectives that we've gone over so far. I've kind of put them all into one place just to kind of help you guys study. Okay, and it's especially useful for helping you study for the conceptual topics. Okay, and so if you'll notice, a lot of the learning objectives that I've posted here, and we have some good examples for today. They're almost written in a form that I can give you as a test question, right? So when we look at the first learning objective, you can see it's describe the utility of step functions for modeling engineering systems. Okay. And so hint, I could give you a problem like that, very similar to that one, maybe not exactly like that on the exam, but very, very similar. So what I always tell my students is that when you're studying for my exams for the conceptual portion, go to the study guide, answer all the learning objectives. So write out an answer to all those conceptual questions as if they were on the exam. And check that with your friends, maybe check it with me if you're not sure. And if you can do that, you're going to be very well prepared for the conceptual portion. Okay. For the problem solving part, like I mentioned, the problems are going to be very similar to the homework. They're going to be easier than the homework. I know the homework problems can be pretty time consuming. But I'm designing the problems on the exam to be, so that it doesn't take you the whole time just to do the arithmetic. Okay. And so for conceptual questions, use the study guide. For the problem solving, study the homeworks, and I would say that's kind of the best way to study for this exam. Okay, all right. Oh, the other announcement I have to make. So Thursday, I fortunately can't come to campus on Thursday, so I have to be at home just because I have some work being done on my home. So Thursday's lecture will be virtual only, and so You can come here. I think you can use the computers here to watch the lectures, but probably you're gonna be more comfortable at home. And so you can view the lecture at home. So Thursday will be virtual, and the office hours will also be virtual Thursday as well. But the exam next Thursday is gonna be in person only. So there's no plans right now to offer the exam on campus, and so please come to campus next Thursday, or at least plan to come to campus next Thursday. Okay, so I think that's all my announcements. Are there any questions about the exam or anything? Right, and so if you have any questions about the exam, the format, or the content, I'm available in all my office hours this week. I don't have office hours today, but I have office hours Wednesday and Thursday, and of course I have all the office hours next week as well. So Monday and Wednesday. Well, next Thursday will be too late. That'll be afterwards. I know, and I know I'm a little bit late in grading your homework too, so that is one of my first priority today. So homework 2 will be graded by the end of today, and you'll have a solution for homework 2 as well. Okay, and for homework 3, I know homework 3 is due this Sunday. On Monday, what I plan to do is I plan on uploading the solutions for homework 3, even though I probably won't grade it on Monday, but I at least want to have the solutions out to you guys so you can use it to study. Okay. Okay, so a lot of announcements today. So definitely if you didn't catch everything, go back to the recording and you can see all of it. A lot of it is okay. All right. So with that said, let's go ahead and get started with the lecture today. We kind of have a lot of ground to cover because of the guest lecture last Thursday. So by the way, I hope you guys enjoyed the guest lecture. That was my first time meeting her. Usually I meet the guest speakers beforehand, but I think because we kind of planned this at the last minute. That was my first time meeting her. She's really cool. So hope you guys enjoyed it. I'm sorry that the recording's not available. We had some technical difficulties in getting her slides to work, so I wasn't able to record the lecture. But hopefully if you guys are interested, you could reach out to her and contact her. Hopefully if you can get an internship at JPL, that'd be okay. So the subject for today, and for Thursday is going to be, we're going to be finishing up our Laplace section. And so today our focus is going to be on step functions. Okay. And sometimes they're called Heaviside functions, but I'll mostly refer to them as Heaviside is probably the name of the guy that discovered this, or at least formalized it in mathematics. Sometimes you'll hear Heaviside function. If you hear that, it's all right. So what are step functions? Well, so first of all, what are we going to use them? Okay. And so when I introduced the idea of Laplace transforms, I think a couple of weeks ago, I talked about the fact that Laplace lets us solve, or it lets us model situations that we can't do traditionally. Okay. And today you're going to get the first chance of seeing that. And so today we're going to learn about step functions, which is kind of the first tool, and then Thursday we'll learn about impulse functions, which is kind of the other one. And so to kind of motivate step functions, let's do an example. kind of a physical, kind of visual example. Okay? Let's consider a common circuit, but let's have a circuit with a switch. Okay? And so the idea with a switch, very much similar to a light switch in a room like this. You can turn the circuit kind of on and off. You can connect the circuit, and you can disconnect the circuit, as you push. And so let's say it's just a simple RC circuit. So we have a resistor, capacitor. We have a switch here. And we have a okay. So RC. Right. So the idea with the switch is that the switch connects the circuit to the battery. Okay. And so when the switch is off, like it is right now, the circuit is not connected to the battery. But when you turn the switch on, then the circuit is connected to the battery and the capacitor will start to charge. Okay. All right. And so whether the circuit is connected to the battery or not gives us two situations. Okay. And we have two corresponding ODEs for those situations. And so our first ODE, let's say this is going to be switch off. And so once the switch is off, then the circuit is not connected to the battery. Okay. And in this situation, we have what's called a discharging RC circuit. Okay. And so the capacitor might have built up some charge, but when it's not connected to a battery, that charge will start to dissipate through the resistor. Okay. And so we have a situation like this. So Q T plus 1 over RC Q to 0. Okay. And so for this situation, this is just a first order ODE. And so the solution for this, we're just going to skip ahead. No problem. Okay. Where Q naught, Q naught is the initial charge on the capacitor. So that's our initial condition. Okay, so we have just a decaying exponential. Okay. But if the switch were on, then the capacitor will start to charge, right? So the battery is providing power to the circuit, and so that's going to charge the capacitor. Okay, and so our governing equation actually looks different. So Q dt plus 1 over RC times Q is equal to E over R. Okay. We're going to assume that the battery provides a constant load. This is a DC circuit. Okay. And so we can solve for this solution. This is again a first order ODE. This one is a linear ODE, so we have to solve it with integrating factor. Okay. Times 1 minus e to the minus t. Okay. So we have two situations depending on whether the switch is on or off, and two kind of corresponding solutions. Okay. All right. And so up until this point, I would say that we could solve, each of those situations individually. We could solve no problem, right? So these are first order ODEs. You can either solve them in the switch off. You can solve that with separation of variables. The other one you can solve for integrating factor. Right? So individually, they're no problem. Okay. The issue is that in reality, you have these two situations, and the circuit could kind of switch between one and the other, kind of very quickly, right? And so, let's say that you have a 8-year-old cousin or something like that, and they love to flip the light switch, right? So you've probably done it before. I've done it before. You go up to the wall, you kind of flip the light switch on and off, and you see the lights flicker. Your parents yell at you, they tell you your disappointment, and then you get feel sad and do other stuff. But anyway, if we were to have that situation in reality where the switch were going on and off, this would be really annoying to solve because we'd have to solve one equation, get the final solution for that, take that solution, make that the initial conditions for the other one, solve that one, and then kind of go back and forth. Okay? And so kind of our traditional methods right now aren't really designed well to handle a situation where our forcing function, which is on the right here, okay, we don't really have a good system for when that forcing function is going to change. And so at the very least, even for just a simple case of going from off to on or on to off, we'd have to solve two different differential equations, which is very annoying. Okay. And for situations where it turns on and off, which is not all that uncommon in engineering, really at all. It'd be really annoying to solve because each time the equation changes, we have to solve a different solution. Okay. And that's going to be right. But of course, I'm bringing this up because Laplace, along together with this new function called a step function, allows us to solve this in one kind of nice framework. And this is where Laplace starts to shine. And so, Laplace really starts to shine in situations where you have, situations where you can turn things on and off. Okay? And we're going to see that in a second. All right. Before we go there, are there any questions on this? Okay. All right. So let's define the step function because that's going to be kind of the key to everything that we do. Okay. And so the step function is basically a function that goes from off to on, okay? And then visually it looks like a step, right? So that's hence the name. And so we usually define it using this variable u, okay? And so what we say is that u of t minus a is equal to, it's a very classic kind of discontinuous function because it's 0. The step function can either be 0 or it can be 1. Okay. And the change between 0 and 1 kind of happens very abruptly. Okay. And so the switch from 0 to 1 happens when t is equal to a. Okay. So up until t, before t is equal to a, the step function we consider to be off. And then once t hits a, that's when it turns on. Okay, so visually it looks like this. So have a time axis on the horizontal axis. And if we denote a is there, so a could be just any constant. So it could be just 1, 2, 3, whatever. That's just the time that we turn it on. Okay. Up until that point, our step function. And then once we hit A, it just shoots up to a value of 1. And it continues on from. So this value here is so that's all it is. And so it's just something that's either 0 or 1, and that transition happens just at one time. Okay. And so what we're going to do today is we're going to combine this together with differential equations and Laplace and solve for situations where we turn things on and off. Okay. And what we're going to end with today is we're going to end with a circuit example. I think not exactly the same as that circuit, but you can see it in action and how that actually affects the solution. Okay. All right. So the first step, before we can actually use this with our differential equations, is that we have to know how to take its Laplace transform. So let's do that. So let's take the Laplace transform of u t minus a. Okay. And so let's go back to our integral form from before. So we take the integral from 0 to infinity of e to the minus st u to the minus a d. And so just like we did 2 weeks ago, we're going to integrate out the t variable and then get it in function. Okay. All right, so what we're dealing with here is a discontinuous function, right? And so the function has one value up until a, and then another value from there, okay? And so when you're integrating a discontinuous function, the best way to deal with that is to just break apart the integral. Because we know the integration is going to happen between 0 and infinity, right? And so let's break up that integral from 0 to infinity into one integral that goes from 0 to a, okay? Because a is when the first thing is going to happen, plus integral from a to infinity. Okay? Remember from calc, I think it's probably calc 1, calc 2. When you have a continuous integration bound like this, you can break it up into separate integrals. As long as the ending of the first integral is where the second integral starts. Okay, so we go from 0 to a, the first integral, and then a to infinity for the second. Okay. So we're going to bring down the exponential term, e to the minus st. Okay. And then from here, we're going to plug in the value for our step function. Okay? And so based on the definition for a step function, when t is less than a, okay, so for the integral between 0 and a, we're going to multiply this by 0. Okay, because that's the value of the step function between 0 and a. And then from a to infinity, our step function has a value of 1. And so, of course, the integral of 0 is just 0. And so this is just going to be canceled out. Okay. And then we have the integral of e to the minus st dt from a to infinity. And so if we evaluate this integral, we, of course, get minus 1 over s e to the minus st, evaluate from 0 to infinity. We plug in the integration bound, we get minus 1 over s times e to the minus infinity minus e to the minus as. Okay. And so we know that e to the minus infinity is going to go to 0. And so we obtain our Laplace transform So the Laplace transform of u t minus a is equal to e to the minus as over s. Okay. All right, any questions on how we obtain that Laplace transform there? Okay. Right, and so this should look pretty similar to you, besides the e to the minus as. Obviously, that's the new thing. So you remember that our very first Laplace transform. And so the Laplace transform of 1, which is 1 over s, right? So if you remember that from okay. This looks very similar. So we have a 1 over s factor there, but then we're modulating it by e to the minus as. And so you can almost say that this is the same thing, except that it's being shifted by this a factor. Okay? And so we'll come back to that in a second, but while we're here, I wanted to point that out just so that you can start to notice that pattern. Okay, but we'll kind of come back to that. But first, I want to talk a bit more about how we can actually use the step function in practice. Okay. And so the main use for the step functions is that it gives us a way to turn off other functions. Okay. And so it kind of looks like this. So let's say that we have a simple function. So say y is equal to sine of t. Okay. We have a simple sinusoid. If we plot this, okay, so we have our t and y axes here. Okay. The plot for this is going to look something like this. Okay. And so we know sine of t is going to be an oscillating function. It starts out at 0, at t is equal to 0, and then it kind of oscillates up and down. Okay. We can turn this off using the step function. So let's compare this to another function. And so just like the first one, we're going to have y is equal to sine of t, but we're going to multiply this one by a step function. Okay. And so we're going to multiply it by u of t minus 2. All right, so let's see what that looks like. Okay. All right, so by multiplying our function here by a step function, what we're basically doing is that we're turning off the function before t is equal to 2. Okay. And so if we mark it, so let's say t is equal to 2 is right here. Okay. Up until that point, because we're multiplying by the step function, up until that t is equal to 2, we're taking 0 and multiplying by sine of t. And so it's going to look like this. And so it's going to be all 0 up until that point. But then after t is equal to 2, then the function suddenly turns on again. Okay. And so it might look something like this. And so, I try to draw this kind of very intentionally. So, you may look at something like this and you may think, that what we did was we took this function, our original function on the left, and we just shifted it over to the right. Okay. I think that's kind of the thing that people get confused about with step functions is that, they think by multiplying by step function, it's the same thing as shifting it over to the right. But that's not necessarily the case. Okay. And so if you overlay these two functions, okay, the left and the right, they should match up exactly after t is equal to 2. Okay. And so kind of a more accurate way to describe this is that, before t is equal to 2, we basically just deleted the function. Okay. We didn't shift it at all. And so we took the function and we basically just took an eraser up until t is equal to 2 and just erased everything to the left. Okay. So there's no shifting that took place. We literally just turned the function off before t is equal to 2. Okay. And so there's no shifting here. Okay. But with that said, we can shift the function. It's just going to look a little bit different. Okay, so I'm going to give you a third function here, and we're going to see how that one is a little bit different from these last two. Okay. And so let's draw the shifted version. So the shifted version would look something like this. And so we have sine. Instead of t, what I'm going to do is I'm going to replace the time argument by our step function. Okay, so our step function argument here is u of t minus 2. Okay. And so I'm going to replace the time argument here with sine of t minus 2 as well. Okay. And so by applying the shift, by basically applying the same shift to the time function as our step, we're effectively shifting the start of the function to when the step starts. Okay. And so this is going to result in a very slightly different graph. If we kind of graph this out, t y. Again, we mark out t is equal to 2. Okay. But in contrast to the last example, we're actually going to shift that starting point over to 2. Okay. And so we know that sine of t just by itself is 0 at t is equal to 0. Okay. But by applying the sine of t minus 2, we're shifting it over to the right by 2. So now, this version, because of the step function, before t is equal to 2, we're going to have 0, just like before. Okay. But once t is equal to 2, then we start our normal sine. Okay. And so you can see if you compare this graph to the unshifted one, you can see here that we have kind of a traditional sine function that starts where the shift or where the step function begins. Okay. Okay. And so before we move any further, because we're going to have a lot of functions with shifted t's. I wanted to show you kind of the difference between these three cases. Okay, so we have our base case, we have our case where we just turn the function off, so no shifting. And then we have the shifted case where we shifted the function over the same amount as the step. Okay, so kind of knowing these three differences is kind of important to us as we move on. Okay. All right, any questions on any of this? Okay. All right, and so speaking of shifting, let's talk about the second shifting theorem of Laplace. Okay. Okay. And so we talked about the first shifting theorem already, and so I think we did that last Tuesday. Okay, so that was called an S shift, right? So we basically multiplied by an exponential function in the time domain, and then that results in a shift in S in the Laplace domain. Okay? The second shifting theorem is the opposite, so we often call this a T shift. Okay. And so the two shifting theorems, the first and second shifting theorem, are almost like mirror images of each other. Okay. And so the idea with the second shifting theorem is that you multiply. Okay. And so if you multiply by an exponential function in the Laplace domain, and so in other words, if we're multiplying by something like e to the minus as, okay. And so in other words, our exponential function has an s in the exponent, okay. What this is going to do is that it's going to cause a shift in the corresponding function in the time domain. Okay. All right. And so let's write this out. All right. And so mathematically it looks like this. And so if we have the Laplace transform of ft, okay, we know this is f of s. Okay. And so f of t there could be almost any time domain function. Okay, so if that's true, then if we take this f of s and we multiply it by e to the minus as, okay. And so the same Laplace transform, we just multiply by e to the minus as. Okay. We know that this is just the Laplace transform of f of t minus a times u of t. Okay. Right, so what we did is we basically multiplied by an exponential function in the s domain. Okay. What that did was it causes the time domain function to be shifted by a. Okay, so not only do we shift the time domain function by a, but then we also have that step function that appears as well. Okay. Okay. All right, so that's the second shifting. So a lot of Laplace, first and second shifting theorem, a lot of it's based on exponentials, mostly just because that's just the form of the transform. Right? And so the integral transform has an exponential in it. And so whenever you multiply by an exponential, it's going to cause some kind of shift because that's just the nature of the transform. Okay, so let's see this in action kind of with a simple example. Right? So is everyone done writing this down? Everyone good? Okay. All right, so let's do a very simple example just so that you can see it in action. Let's use our same function from before. Okay, so let's take our simple sine function. Okay. And so if we take the Laplace transform of this, Laplace transform of sine is going to be 1 over s squared plus 1. Okay. And so let's shift this. So let's multiply, or if we multiply, if we multiply y of s by e to the minus 2s, then what we get is e to the minus 2s divided by s squared plus 1. Okay. And then from here, we can take the inverse Laplace. Okay. Right. And so when you come across expressions like this, with an e to the minus, as in the Laplace domain, it can be kind of, I think, a little bit confusing to try to take the inverse of this because there's none, if you look at the Laplace table, there's nothing like this. Okay. And so let me show you a technique that I like to use. And so when you're taking the inverse Laplace of something with an exponential, what I like to do first is I first take the inverse Laplace of the function without the exponential. Okay. And so what I'm going to do is I'm going to take this e to the minus 2s. And the good thing about Laplace is that this exponential always appears as just kind of like a coefficient. Okay, so you can always kind of factor it out. And e to the minus 2s multiplied by 1 over s squared plus 1. Okay. And so the nice thing about this is that, what's inside the parentheses right now, we can take the inverse of that. Okay. We literally did it just up here. Okay. And so the inverse of this, as we know, is sine of t. Okay. So what we have is something like this. Okay. So we have e to the minus 2s times sine of t. Okay. This kind of looks like a weird expression because we're multiplying the Laplace by a time domain function. So normally this is not something you would do, but in my head, this is kind of how I process this. So I thought it'd be useful for you. And so once you kind of take the inverse of I call it kind of the base expression, then what you do from there is you apply the t shift. Okay. And so we know, based on this exponential, we're going to have a t shift of 2. Okay. And so basically, everywhere that you see t in your base function, you're going to replace it by t minus 2. Okay. And so here our base function is just sine of t, but instead of sine of t, we're going to do sine of t minus 2. And then the other thing we're going to do is we're going to multiply that by the step function. Okay. So this is the Laplace inverse of e to the minus 2s divided by s squared. Okay. All right. So that's kind of the two-step process that I follow in my head. So, when you're taking the inverse Laplace of these terms with exponentials, do kind of the base function first, because that one you can read off the table. And then after you take the inverse of the base function, then you apply the t shift to that result. Okay. All right. Any questions on this? Okay. All right. So let's start applying this to actually solving some differential equations. The first thing we're going to do is we're going to talk about square waves. And so square waves are basically going to be a combination of step functions to produce the following waves. Because in reality, when you're solving these kind of physical systems, very rarely do you have a forcing function that just continues on to infinity. Right? Eventually, a lot of these forcing functions turn on. So, we like to model that. And so a square wave read this. All right, so a square wave is going to be 0 at first, and at some point it's going to turn on and to continue on for a while, and eventually it's going to turn off. Okay. And so we'll call this time A1. A1 is when the time turns on, and A2 is when the wave turns on. Okay. So maybe square wave is not the best word for it. I guess rectangular wave is probably a more accurate term, because the wave itself doesn't have to have a length of 1. It just looks like a rectangle. Okay. Okay. And so we can model, model this using a combination of step functions. All right, so first thing that we notice is that the wave turns on at A1. Okay. And so if we look at just A1 just by itself, right, that just looks like a regular step function, right? And so we can model this by taking a step function of u e minus A1. Okay. And then we know the wave turns off at A2. Okay. And so one way that we can model the wave turning off is by subtracting another step function. Okay. And of course, the step function is going to start at A2. So we have minus u of t minus A2. Okay, and so if we combine these together, our total function here, u t minus A1 minus u of t minus. And so you can subtract step functions like this to create kind of this square wave, okay, or rectangular. Okay. Okay, and so with this kind of in our tool belt right now, we're kind of ready to start doing functions that can be turned on. Okay. So let me skip ahead to the circuit. Okay. So let's do, we are going to do the RC circuit. So let's do the RC circuit. And so we're going to do the RC circuit with a switch. All right, so we're going to have the same diagram as before. We're going to have a battery, DC battery E. We have a resistor R. Capacitor. And so our governing equation here is we're going to have a time derivative of the charge on the capacitor. So that's dq dt plus q divided by RC E of t R, where E of t is going to be the charge to be divided by the battery. Okay. And so our E of t here is going to be divided by a discontinuous function. Okay. And so we're going to do a situation where the square wave, or we're going to use a square wave for this function. Okay. And so initially, when time first starts, the battery is going to be disconnected. Okay. And so E of t is going to be 0. Okay. When t is less than a, excuse me. Then when t is equal to a, we're going to connect the battery. So that's when the switch is going to be on. Okay. But after a certain point, the battery is going to switch off. Okay. And so we'll call that time B. And then at time B, you know, we switch off, and so the charge from the battery is going to be 0. Okay. And so since this is a first order equation, we also need an initial condition. And so let's say that in this case, the capacitor is going to start with some initial charge. So the initial charge on capacitor. Okay. And so before we start solving the problem, let me kind of tell you physically kind of what's going on. And so first, you know, our capacitor is going to start with some charge. Okay? But since in the initial phase of the problem, the battery is disconnected, and so what's going to happen is that that capacitor is going to start to discharge some of this charge. Okay, and so that charge is going to go down. But then when the battery is connected, that charge is going to come back up. Okay, and then we disconnect the battery, and then the charge is going to start to decay out of that. And so we're going to kind of do. We expect kind of the charge to kind of go up and down depending on when the battery is connected. If we were to solve this using kind of the normal methods, we would have to solve 3 different problems, right? Because basically what's happening is that the forcing function is changing 3 times. Okay? So basically every time our forcing function changes, that's a new equation that we have to solve. Because each one is going to have different initial conditions. And so, you know, a problem like this would be very annoying to solve in kind of the traditional way, because you'd have to solve 3 equations with 3 initial conditions, and you know that's no fun. Okay? But what you'll see is that with Laplace transforms, that this is done very easy. Okay, let's start solving this problem. And so the first step, whenever you have a discontinuous function like this, is to represent that function using step functions. Okay. All right, so let's do that first. And so we know that our our forcing function here is basically exhibiting, or it's basically the same thing as a rectangular wave. Okay, so at a certain point, it's going to turn on, and then after a certain time, it's going to turn off. Okay, and so we know it turns on at t is equal to a. Okay. And then we know the function is going to turn off at t is equal to b. Okay. And so if we use kind of the same kind of theory that we did up here, then representing this with step functions, we're going to have u of t minus a. Okay, so that's when the battery turns on. And the battery is going to turn off at u of t minus b. Okay, so we're going to subtract. Put myself in the eye. We're going to subtract u of t minus b. One thing that we didn't do in the previous example is that we didn't have another constant, right? So we just assumed that it was just one down front. But we know that the value for e here, for t, is going to be e. And so I'm going to multiply this by e, which is kind of what that constant is. Okay. And so this is now E of. All right, so let's plug this into our ODE. And so our ODE was dQE plus Q over RC equal to 1 over R, or I should say E over R times U of T minus A minus U T. Okay. So this is really nice right here. So what we've done is we've taken our discontinuous forcing function and we've represented it as one ODE. Okay? And so when we solve this with Laplace, we just have to solve one problem, and then we're good. We're good from there. Okay. So now that we've represented the forcing function as a using step functions, we can now take the Laplace transform of the entire. Okay. We're going to take the Laplace transform of dQt plus Q over RC equal to E over R T minus A minus T minus A. Okay. And so just like we usually do, let's take the Laplace transform of each term individually. Okay. But first we have the Laplace transform of dq dt. So this is going to be S Q of S minus Q of 0, okay, plus Q of S C is equal to E over R. We take the Laplace transform of U of T minus A. We know this is going to be E to the minus AS divided by S minus. Then we have the Laplace transform of U of T minus B. And so this is E to the minus BS. Okay. So let's plug in the initial condition. And so the initial condition Q of 0 we know is Q naught. Okay, so that's the initial charge on the capacitor. And so let's move that over to the other side of the equation. And then one more step that I'm going to do here is I'm going to isolate Q of S, right? Remember, the second step after when you're solving these ODEs with Laplace transform is to isolate the solution variable. Okay. And so if we do that, we have Q of S. This is multiplied by S plus 1 over RC. This is equal to E over R times Q to the minus AF divided by S minus E to the minus BS divided by S plus Q okay. So let's solve for Q of S. And so we're going to divide both sides by S plus 1 over RC. So we do that, we get Q of S is equal to E over R times E to the minus AS divided by S plus 1 over RC minus E to the minus BS divided by S times S plus 1 over RC plus U naught divided by S plus 1 over S. Okay. All right, so now that we have it in this form, we can, all we have to do here is take the inverse. But right now, we have a term that doesn't show up in our tables. Okay? So remember, ignore the e to the minus as. We can apply the shifting at the end. Okay? But besides that, we have a 1 over s times s plus 1 over rc. So this term we need to apply partial fraction in order to get into a form that we can use. Try to write a P with my mindset R. Okay, so let's do partial fractions here. So again, I'm going to ignore the e to the minus as up top because we can apply that shifting at the end. Okay, and so we have 1 over s plus 1 over rc. And so we want to split this up into two different fractions. We're going to have big A over s plus big B over s plus 1 over r. Because the idea is that, if we split this up into those two terms, we can take the inverse of that using the table. Okay. All right. I'm just going to do the partial fractions here pretty quickly, just because we've done this several times before. Okay. And so I'm going to multiply by the denominator here, and so we have 1 is equal to a minus s plus 1 over rc plus bs. Okay. If we group those terms, we have s times a plus b plus a times 1 over c. Okay. And so if we set up our equations here, our s equation a plus b, a plus b is equal to 0. Okay. And for our constant term here, we have a over rc is equal to 1. Okay. And so what we get from this is a is equal to rc and b is equal to minus rc. Okay. And so therefore, what we get is 1 over s plus 1 over rc is equal to rc over s minus rc over 1 plus 1 over s plus 1 over rc. All right, so now it's in a form that we can take the inverse of this. And so let's take the inverse. Okay, and so just like we usually do, we're going to use our table. Okay, and so first we have rc over s, and so the inverse of that is just going to be rc. Okay, but the inverse of 1 over s is just 1, and so we multiply that by rc, we end up with just a constant rc. Okay. Then we have rc over 1 plus 1 over rc. Okay. And so the inverse of this is going to be rc times e minus t over rc. Okay. So let's take this expression here and let's plug it back into our q of s expression. Okay. And remember, we haven't applied the t shift yet. Okay, so this is before t shift. Okay. So q of s equal to E over R times RC RC minus RC minus T over RC. This is multiplied by e to the minus AS, or e to the minus AS minus, same thing, RC minus RC, e to the minus T C, e to the minus BS. Okay. And then we have our term for the initial condition. So we have Q naught over S plus 1 over RC. So this expression is kind of a weird one right now because we have combination of S and T. Okay, that's because we're kind of in the middle before we apply the T shift. Okay, but I like to write this out first because if you try to do everything at once, like you try to do the inverse along with the T shift at the same time, I think it could be a little bit confusing and you might miss a shift or you might miss a term. Okay, so this is kind of a, you know, in reality, you know, if a mathematician saw this, he said this would be an abomination. Okay, because we have both T and S going on, but you know, this mentally, this is kind of what I do, just to kind of make sure I don't get confused. Okay. Okay. And so from here, we can see that we have a term that's going to be shifted here. Okay, so we need to apply a T shift here. And then we have another term that we're going to apply a T shift of. Okay. But that T shift is going to be B because that's the term, that's the coefficient that's in the exponent. Okay. And then of course we have this last term here, which we haven't taken the inverse of, but this is fairly easy to take the inverse of. Oh. And so once we do all of that, then we'll have completed the problem. Okay. So let's do all of those things. So we have Q of T equal to E over R multiplied by. Let's take that first expression there and apply a T shift of A to it. Okay. So basically everywhere that we see T, we're going to replace it with T minus A, and then we're going to multiply it by our step function, right? U of T minus A. Okay. And so we have RC minus RC E. Here we have a T, so we have, instead of e to the minus T over RC, it's going to be minus T minus A divided by RC. Okay. So all I did for that first term there was that, you know, instead of e to the minus T, I did e to the minus T minus A over RC. Okay. And then we multiply it by our step function, and so we multiply by U of T minus A. Okay. Then we're going to subtract the exact same thing for B. Okay. Or for the second term, excuse me. So we have RC minus RC e to the minus T minus B divided by RC. Okay. And then we're going to multiply that by U of T minus B. Okay. And then we're going to add Q naught. And then we're going to add our initial condition term. So there's no T shifting there at all. So there's, you know, we don't have to worry about that. We just take the inverse straight up of Q naught divided by S over 1 plus RC. So that's going to be Q naught E the minus T over RC. Okay. No shifting there at all. Okay. Any questions on this part here about how we obtain that result? there's a lot of stuff going on. So there's definitely a lot in the detail. So definitely go through this. When you're reviewing this later, definitely go through it slowly and see kind of where all the shifts and where all the inverses kind of fit. Okay. Okay. All right. So last thing I'm going to do here is I'm just going to simplify this expression a little bit because you can see that we have R and C everywhere in this expression. Okay. And so the R is going to cancel out, so we can factor out an R out of every single one of these terms, and that's going to cancel out with an R down there. Okay. And the last thing I'm going to do is I'm going to take the C and then factor that out in front. Just to clean up the expression a little bit. E over T equal to E times C times 1 minus E to the minus T minus A divided by RC times B A minus 1 minus E to the minus B divided by RC U of T minus B plus Q naught E to the minus T over RC. And that there is our final solution. Okay. So it's kind of a mess still, right? And so I think I hyped up today by saying that you can solve these problems with Laplace. Unfortunately, because of the discontinuous nature of the forcing function, you still end up with a pretty ugly looking result, at least mathematically. Okay. But where this really actually shines is if you actually plot this. Okay? And so of course, this is going to be annoying to plot because you have a bunch of shifted functions here or there. But if you look at the plot, it actually looks really cool. And it actually looks kind of consistent with kind of what we believe the function would look like. I'm just going to show you the plot really quick just to kind of end today. Okay. And so we know the plot is going to start at Q naught, okay, because that's the initial condition for the problem. And remember what we said initially. So initially the battery is disconnected from the circuit. And so the capacitor is going to start to discharge. Okay. And you actually see that exactly here. So up until T is equal to A, okay, all we have is just this term. Okay. And so what you're going to get is kind of a decaying exponential. It looks like this. Okay. Then at T is equal to A, then the battery is going to be connected, and then the capacitor is going to start to charge. And so at T is equal to A, you kind of see it kind of go up like this, okay, up until T is equal to B, okay, when the battery is going to be disconnected again, and then you have the exact same thing happening where the capacitor is going to start to discharge. Okay. And so in this one function right there, you kind of capture this very complex behavior of turning on and turning off. Okay. And our graph kind of represents that. Right. Of course, our graph here has some kinks into it, right? So we have kind of a discontinuity here. Well, I would say the derivative is more discontinuous there. And we have a discontinuous derivative there, right? But the fact that we can solve this all in one problem using Laplace is something that's really, really cool. And something that we couldn't do before, because before we were just limited to just purely continuous problems. Okay. And sometimes when I look at this graph, I think it looks like a show. All right, any final questions on this before we wrap it up for today? Okay, all right, so that's it for step functions. And so on Thursday, we're going to cover impulse functions. Okay. And so with this, you should be able to do problem 4 on the homework. So I definitely wanted to go through this example. I think problem 4 on the homework is quite similar to this. And then after we go through the content on Thursday, you'll be able to finish it up. Okay. All right, so thank you guys for coming today. Hopefully you guys enjoyed the lecture today. And I will see you guys on Thursday.